Today we're going to look at the definite integral, and which is based on the fundamental theorem of calculus. The definite integral is a pretty basic process once you integrate, but the key is understanding what the definite integral means. So let's review what we're doing when we find the integral of something. If I take a function f of x and I integrate that, remember, basically what I'm doing is finding what my original function would have been. So technically, if we start with the function, that would have been our derivative function, and when we integrate back, we get our original function. So let's talk about what that means graphically. If I take this curve, which would represent a derivative function, and integrate it, then when I find f of x at a, so when I find f of a, or I find the integral of f prime of a, so those would be the same exact thing, what I'm really doing is finding the height of that bar. And when I find the integral of f prime of b, which will give me my original function f of b, I'm finding the height of that bar. And when I find the integral of, and let me switch colors here, but when I find the integral of this line, or this point, I'm finding the height of that green line, and the next point, I'm finding the height of that black line, and so on. If I keep finding the heights of every single one of these points, then what I'm getting is a whole bunch of, if you can imagine, very, very narrow rectangles of unit 1 and of width. So each one of these has a certain height. Each one of these has a width of 1. So the width of that rectangle is 1, this rectangle is 1, and so on. Then what we have, this red line right here, if I exaggerate it, is a rectangle with width of 1 and height equal to the integral of that function at that point, or also equal to f of b. So integrating a function will give us the height of that segment that goes from the x-axis to the curve. And if we do that at intervals of 1, now you don't have to specify, well, is that 1 inch or is that 1 centimeter? It's an itsy bitsy unit of 1. Maybe it's a micrometer. So very, very tiny. The wider your 1 is, I could technically draw a rectangle that's this wide, but notice that that piece of the rectangle isn't touching the curve, and so we're not filling all of that space. Our goal is to fill this space with itsy bitsy rectangles, and if I keep filling this space with itsy bitsy rectangles, and I find the area of each of these itsy bitsy rectangles, well, the area of this rectangle is simply the base times the height, which would be 1 times the integral, or the h, I'll just write the h, but that's the integral. So if I know that my area then of each itsy bitsy rectangle is equal to really the height of that segment, then I could find the area of this odd-shaped object by simply knowing the function described by that green line. And if I know the function described by that green line, I could integrate it to find the function values up here. And when I do, I have a whole bunch of areas, and when I add those areas up, I now have the area under the curve. And so that's the whole concept of what integration does, is that it helps us to find the function value, and then by applying the concept of a rectangle of unit 1, we can add those all up. And so that's what the fundamental theorem of calculus says. So let's take a few notes here. Remember that when you integrate, you are finding a function from the derivative. So if you have a function that represents the derivative, you can find the actual one, and that equals the height of the line. And so then we can fill up the space, and if we want to go from A to B, do you see how I just wrote the A and B? From A to B, we can find the heights of all the lines. We can say those are rectangles with a unit 1 base, and we can add them all up. And that equals the total area. So if this green line were to represent money flow of my company, then this area right here would represent the total money flow from a certain point A to a certain point B. So we use the concept of total a lot when we get to our applications. And so let me formalize that, and here's how we write it. This is a fundamental theorem of calculus. And watch as I write and hear what I say to go with it. The integral from A to B of a function. Now we don't write the little derivative sign there because any function you take, if you integrate it, you're saying that that original function represented the change, and by integrating it you get your original function back. That can also be written as the integral of the function evaluated from A to B. And the last way we write that then is capital F, which means the integrated function from B of B minus the integral function of A. Now, why do we do B minus A? Because what we're simply doing, if I scroll back up, what we're simply doing is finding the distance here. So we are taking the upper limit B and subtracting the lower limit A. And that is because we are really, if it boils down to it, taking that piece right there away. From here to here is not included. So if we take from here to B and subtract from here to A, then we have our area that we want. So that's our whole concept there. So let's put that to use. Oh, before we put that to use, let me talk just about a couple of basic concepts. One is that if your integral for some reason is written backwards where the B comes first, then you're actually going to get a negative answer of if you go from A to B, because you're subtracting little minus big instead of big minus little. So we would typically rewrite it and do the negative of A minus B. All of our integral rules apply. One other feature that you can do is, what if we wanted to take a long trip? We wanted to go from A to C. And this is when you have something like a piecewise function, or just something where there's something weird going on. For example, here's a good example, I think. Let's say A is here and C is here. What you're going to learn next unit is that when pieces are above or below the x-axis, that might make a difference in your application. And so if we knew we wanted to go all the way from A to C, what we would want to do here, and right now you're not really sure why I'm suggesting this, but because that first part's above and the first part's below, we might want to break it up in our next chapter. And so you can actually take a pit stop at B. So all I'm saying is, if you might get tired along the way, you can do the integral from a to b, and then you can do the integral from b to c, and you get the same answer. So you can break things into pieces. Another reason you might do this even more than that, because that maybe confused you a little bit, is if we had a piecewise. And so if we wanted to go, if we wanted this area all the way to this area. Well, those are two different equations. So we would have to do a to b and then b to c and then add them together. So that's rules that apply. And so let's do a few examples where we plug in the or we actually use the definite integral concepts. First example is the integral from 4 to 8 of 2 plus 3x dx. The integral from 4 to 8 of 2 plus 3x dx. So the first thing we're going to do is we're going to integrate just like we did before. Now remember, when you integrate, you increase the powers. So the integral of 2 plus 3x equals 2x plus 3x squared over 2. And we have to evaluate that from 4 to 8. And so to evaluate that from 4 to 8, the first thing we do is we plug in 8 everywhere. And sometimes you might want them in parentheses, because then we have to subtract what we got when we plug in 4. So be extra careful with that subtraction thing on the end there. Alright, so we have 16 there. 64, 32 times 3, 96 here. Minus 8. 16 divided by 2 is 8, times 3 is 24. So we have 16 plus 96 minus 32, which I believe should give us 80. Okay. Now, what did we not do with this integral that we've been doing all along? Hopefully you recognize that I don't have a plus c. And let me show you why I didn't bother. So where's the c is the question. Let's take a very simple integral from 1 to 5 of just 7. Let's just do the integral of 7. Alright, so we're going to integrate that, which gives us 7x plus c. So let's put our c in there like we normally do, and we have to do that from 1 to 5. And so let's plug in. So first we're going to do 7 times 5 plus c minus, and now we plug in 1, 7 times 1 plus c. And so we get 35 plus c minus 7 minus c. And as you can see, c is always going to subtract out. And so when you have a definite integral, you will not have that plus c in the final answer, because through the process you are able to cancel that out. So I just wanted to point out what happened to good old c. Let me do one more example, and they don't really get any more difficult than what we're seeing. It's just a matter of being careful with how you put stuff in. So let's just do the integral, so number 3 I guess, the integral from 0 to 3 of the square root of 3x dx. I like to write that as 3x to the 1/2 dx. Don't forget here that we have to make sure that we have the dx represented as you learned from before. So if u is 3x, then du is 3dx. So I'm going to have to put a 3 here and a 1/3 out there. And so now I can integrate this. Maybe you like to write this as 3 u to the 1/2 du. And notice I didn't put the definite integrals on there because those are for x's, so I'll wait till I get my x's back. And so we have 1/3, increase the power here by 1, divide by the new power. And when I divide by the new power, I'm going to really multiply by 2/3, so that's going to come up here as a times 2/3, which is going to give me 2/9 u to the 3/2. Now we can plug in our 3x again, so we have 2/9 3x to the 3/2, and we have to evaluate that from 0 to 3. And so now we plug in. So 2/9, 3 times 3, 3 times 3 to the 3/2 minus 2/9, 3 times 0 to the 3/2. 3 times 3 is 9. The square root of 9 is 3. 3 cubed is 27. So this is 2/9 times 27 minus 2/9 times 0. 9 goes into 27 3 times, so it looks like my answer should be 6. So the definite integral is just that process of making the substitutions and actually finding out the area under the curve or the total value. So if you would go in your calculator and graph 3x to the square root of 3x, it looks something, still is going to go through 0, so it looks something like that. And we wanted to go from 0 to 3, so what we just did was find the area under that curve or the total value of all the money I made this month, next month, the next month, the next month, the next month. So this is adding up all the total values that I made each day in the last 3 months and telling me what my total is. So area under the curve also helps us find total. So just be extra careful paying attention to your values, making sure that the highest value or the one farthest to the right is on top, and if not, you have to switch it, make the negative, and that you can break it into pieces if you need to. And we'll be practicing this and especially using it on applications. You can do this on your calculator. We'll talk about that shortly. At this point, practice some by hand, but I encourage you to, on your calculator under the math feature, if you have a TI, is look for what's either called the definite integral or the integral sign. Depending on which model you have, it looks a little different. But there are some cautions, and so you can try it with some of these basic ones, but your answers, when we get to applications, it's not as direct. So right now you could use it to check your work because the calculator will give you these exact answers. So try to figure that out, and we can certainly be talking about that in a future little lesson. There are also tutorials in your Blackboard under the tutorial button that take you to the actual TI tutorial area that would show you how to use that feature. So hopefully that will help you as well. So here's definite integrals. We will definitely be using this a lot as we proceed into our applications during the next unit.